Okay, so going on to different kinds of radiation. I mentioned this a little briefly yesterday, but electromagnetic radiation would be radiation that is both electricity and magnetism. So light, X-rays, microwaves, gamma rays are all that same form, where you have magnetism in one wave, electricity in another wave that moves through. And based on the frequency of that, we see different kinds of light colors, or we get microwaves or radio waves or X-rays. So in this, you can see that UV, or visible light, is only a small part of the spectrum. Could you all close the blinds a little back there so it'll be easier to see the notes?
Is this still 5.1?
Yes, we're on 5.1. So the visible light that we see is only the small sliver. And the rest is radiation that's invisible to us. Now, it can still affect us, but we can't see it. So infrared, below that, UV, ultraviolet light above that. So infra means below, it's below red, ultra above violet.
So, has any human ever like had a malfunction in their makeup to be able to see some infrared UV?
I haven't heard of that. Now, it's possible that it can happen. What I have heard is that there are mutations that happen where you can see more colors than the average person. So, you can see like 64 million colors usually, and they can see more than that many colors. They can see more shades of pink, for example, and red. I've heard of that mutation happen, but I have not heard of mutation where you can see UV or infrared light, but it's possible because we have animals that can see those things. So it's possible that humans could also have that. But I haven't heard of that case personally, but I would imagine that that's a possibility. You can see on here the various wavelengths. And so all that separates, say, an X-ray from microwave would just be the frequency. They're all made of the same stuff. They're all made of photons, little packets of energy traveling in waves. So what makes a red light versus a blue light would be the wavelength or the frequency of the photons moving. It shows you, you can see the butterfly, the pinhead, bacteria. That's telling you the wavelength. So for microwaves, it's about an inch to about 6 feet in wavelength. For radio waves, it can be hundreds of feet, even 1,000 or so feet in wavelength. And then you can see that for visible light, it's on the order of the size of a cell or a virus in wavelength. And then we have ones that are much lower in that. We're looking at gamma rays and X-rays. That's in the size of an atom or some type of particle, the photons or the protons and neutrons that make up the atoms. So the smaller the wavelength, the higher the energy. And so on here, which one is the highest energy radiation? Gamma. Gamma is the highest energy radiation. Did I tell you before what they use gamma rays for? They may know what they use gamma rays for. I think I heard it back there.
Radiation.
Radiation, which is
Cancer.
treatment. Yeah, they use it to treat cancer. So when they say radiation treatment, what they mean is gamma rays. So they target gamma rays in the cancer, and it destroys the cancer cells. Now in the process, though, it does also destroy other cells, but the idea is to destroy just the cancer cells. Now it's radiation, and radiation can cause cancer. So there is a risk of causing cancer, but you already have cancer to begin with. So it's the risk is pretty low because you already have it. And radiation treatment is a last resort. That's when you can't have surgery. You have to use radiation at that point. Usually it's along with chemotherapy. Usually they go together. So there's a spectrum of radiation. And this spectrum would include visible light along with X-rays, UV radiation, gamma rays, infrared microwaves, radio waves. Infrared is used in your homes. If you have a motion detector system in your home, you have, you see the red lights usually in the corners of your house. They shine laser beams, or it looks like laser beams, it's infrared light through the house. And when you break the beam, the alarm trips. Or your garage door has these too. At the bottom of your garage door, they have these two little black boxes. Have you seen that with red lights in the black boxes? And it transmits a beam of infrared light across. You can't see it. If you break that beam, then your garage door stops closing. And so if you want to run out of your garage and have the garage door close, you have to jump over that beam so you don't break it. It keeps on closing. Does everybody have that one down? So we talk about light as being a wave, but the wave model of light cannot explain a few things. And so we know that there's more than just a wave to light. So a wave model cannot explain why when you heat up something like iron, for example, I'll go back to that in a second. But when you heat up iron, it glows different colors. It glows red, then it goes on to glowing orange, and then what's next after orange? Have you seen that before? When they heat up iron, it goes from red to orange, then it goes on to a blue to a white color.
But aren't there also like purples involved? Like
Sometimes it can make a blue color.
because I heard that people of old would weld. Also, they would like to weld things together. They would put them in a forge. But when they started glowing different colors, they had a different color for each thing. Like purple for plows, red for rakes, and different things.
So different materials glow different colors. And so iron would just have a certain colors that would glow. But if you had different metals, like cobalt, for example, you have more of a blue color. Copper would make a green color glow. So different minerals would cause different colors. That's why you'd see that. But they couldn't explain, with the iron example, why iron only glows those colors. Why don't you ever see green glowing in iron? Why don't you ever see a purple glowing in iron? They couldn't explain that. You only ever see iron go from, red to orange to white. Yeah, Maria? Maria?
Does this have to do with the electrons or just the light?
Yeah, it does do the electrons. Yeah, that's right. That's why you only see certain colors. And we'll talk more about it in detail later in this chapter, but it has to do with the orbits of the electrons and why you see certain colors.
And is there like many different types of electrons? Like, or is it just like one, like all electrons are the same?
Yeah, all electrons are the same, but they're different energies. And so they're all the same size, all the same stuff, but they're in different energies, going at different speeds. And that's what makes them act differently in different situations.
So the more speed, the more energy?
Right. And the further away from the nucleus they are, the more energy they have too. So those are two reasons why you have different kinds of, so electrons are all the same stuff, all the same size, but different energies based on how fast they're going.
Okay.
Do you have a question, Maria?
How do you make glass?
How do you make glass? You melt sand. So when you heat up sand to high temperature, it melts and it turns into glass as it cools back down. And you can see on the ocean or on the sea shore, lightning, when it hits sand, makes glass. So lightning heats up the sand, melts it, and then as it cools, it turns into glass.
Is that, wait, so there's glass like all over the beach?
Not all over. I mean, but you definitely can see it after a storm, especially.
Would it be like a little ball of glass?
Yeah, it's kind of like, it's usually like, yeah, it can be a ball. It's generally more of just like, kind of like a splash. Like you can imagine like liquid splashing and like coming out and solidifying.
So like if
That's
you break the glass thing on the floor.
kind of, although it's
break it.
smooth. Like
Have
it,
you ever poured water on like sort of dry sand and you can see the water where it goes? Kind of like that.
so it's like in a regular shape. It's just like a bumpy, but it's not going to cut you. It's usually pretty smooth, but also very bumpy.
So could you take like a cup of sand and just melt it over with like a stove?
Well, not a stove. You have to be higher than a stove.
Like a blowtorch?
Blowtorch could, with the right blowtorch. Now you have there's different kinds of blowtorches. But acetylene blowtorch would be high enough to melt it. Propane
Like
is
that?
not. That's propane.
Oh.
It's you need
Are we gonna
but
make glass?
no, I don't have the right equipment to make it. It's not. It'd be really dangerous to have molten sand in the classroom, so we can't make it. I don't have the storage material for it. But I know, Renaissance fairs especially show glass blowing, and they show, they show how the process. So you have usually a long pipe, like a 3 foot or 6 foot long pipe, and they usually twirl it around a lot. And that's usually, they usually don't use their mouth, but they usually twirl it around a lot.
So they use like, whatever the centrifugal force. or
Yeah,
whatever.
exactly. Centrifugal force. Yeah, that's right.
So you know how like sugar, can't sugar also do that? Like you melt it and you can blow it. So does
Yeah.
that act the same as glass? Other
Kind
than, like,
of, although it's not, I mean, it's similar. Now sugar doesn't dry like clear like glass does. Sugar dries, caramel, so we can make caramel that way where you're melting sugar and it turns into caramel. So it dries pretty hard, but it's not usually clear. I mean, it can be if it's really, really thin. And that looks more like a lollipop, for example, would be that. Like where you can make a clear lollipop where you just melt sugar. But generally it's going to dry pretty hard and opaque and not clear like glass. But yeah, it's kind of similar to that in some ways. That's how you make certain kinds of candy. So you make suckers, like Jolly Ranchers, for example. That's pretty much what you're doing in those situations.
So like when there's like glass blowing, when they like add the color to the glass, what do they use? Is it like?
Just different metals. I mean, so yeah, they can use different kinds of dyes, different kinds of metals will cause different colors to form.
Do they like put it in the sand or do they put it on glass? Like as in,
Either way, it wouldn't make a difference. Most likely the sand would be easier, I think, to do it before they, but either way, you'd have the same result. So what they realized with that observation is that energy can only be lost or gained in a certain amount of numbers. So a quantum is the minimum number that you can transfer with energy. Minimum amount of energy that can be transferred through an atom. It's kind of like you think of it as money. You can lose 1 cent or gain 1 cent, but you can't lose half a cent. So the cent is the smallest transfer unit that we have for money. And that's kind of like how it is for atoms. Like a quantum is like 1 cent, where you can there's the smallest amount of money you can transfer. And so for energy, it's the same kind of thing. You can't transfer half a cent, you can't transfer half a quantum. You can transfer 1 quantum or 2 quantums, but not half of one. So based on that, they have this equation which helps relate energy to wavelengths.
So how does that relate to like quantum mechanics?
Yeah, quantum can also just mean really, really small things. So quantum mechanics just deals with the very small, like things like electrons, protons, and neutrons.
What does the E stand for?
Energy. So E is energy of a quantum. So this is how we measure a quantum, is in this equation. Energy equals H, which is Planck's constant, times the frequency. So that's not V, that's nu. That's the frequency of the light. Yes.
This is E quantum, but you said define the quantum, you do energy.
Yeah, quantum is the energy, is the energy that can be transferred.
Wait,
And so energy of a quantum would be the energy you can transfer.
what is the 6.2?
Wait. That's Planck's constant.
So what is it though? Like, is it like a light wave? It's not a light wave because that would be 3.
Planck's constant is just a number. It's just like constants are just numbers.
Okay.
Like pi is a number.
So it's a random number they made up,
Well, it's
or do you
not
have something?
random. It's through experiments. They determine that has to be multiplied to get the right answer.
Oh. It'll take a lot of trial. and error.
Yeah,
What is V again?
frequency. But Emma, what was your question about?
Like if you were to say it like how would this be in a question that you'd have to answer?
They would ask, they would say for a certain frequency of light, what is the energy that can be transmitted?
So what does quantum have to do with it?
So quantum is the minimum energy that can be transferred. And so that would basically just be energy that can be transferred.
What's the JS?
Oh, joules per second, or joules times seconds. So joules is energy, and joules times seconds is the unit.
So H is a measure of
Well, H is just a constant, so it's just a multiplying number.
Oh, so
Yeah, it's
not
like
a
pi,
measure of
think
energy.
about like, how do you find the area of a sphere? Or, it's 2 pi r, right? So, well, sorry, not area of a sphere. Wait, yeah, area of a circle, area of a circle, area of a circle. So you use pi r squared, to get the area of a circle, right? And so pi is just a multiplying constant you get to get the area. Well, it's the same kind of thing here. Think of it as pi.
So is energy and quantum, like, are those connected?
They are connected. Quantum is the minimum energy that it's like saying money versus a cent, right? So cent is like quantum, whereas the minimum amount you can transfer.
So is that what the equation is trying to find the minimum?
Exactly. Yeah. So based on experiments, they found that equation. Einstein, a little bit later, this won the Nobel Prize when he discovered this, the photoelectric effect. He observed light rays, when they hit metal, they eject electrons off the metal. That's why metal is so shiny. When what you're seeing in the shine of metal is electrons jumping off the metal surface. Electrons cause things to shine or to glow. So when light hits metal, electrons are bumped off, but only when certain frequencies of light hit the metal piece. Did you get that down? So Einstein made several discoveries that should have won him the Nobel Prize. 1905, he made 5 discoveries that all could have won the Nobel Prize. But he didn't win one until 1928. He was shut out of Nobel Prize because they were very anti-Jewish at the
You know
time.
who won the Nobel Prizes instead of that?
I'm not sure. They shouldn't have won them. They didn't deserve. I mean, Einstein was more deserving than the ones who did win them. But you had at the time you had Hitler coming to power. You had a lot of anti-Jewish sentiment in Europe, and people didn't want to award prizes at the time to him because he was a well-known Jew. And so it's really sad that that's what happened for so long. But he should have won several, and he only won 1 Nobel Prize. But thankfully he did, not just because he deserved it, but also because, as you saw in that video with Einstein, he divorced his wife, and the agreement was in the divorce that he would give her money after he won the Nobel Prize. Like that, when he won the Nobel Prize, he would give her that money. And which is pretty, if you think about it, that's pretty presumptuous. But he said, when I win a Nobel Prize, you can get my money. And that was just the agreement they had. And so thankfully that happened because she then got what she needed to help support the kids and continue on. But he should have won several because of his discoveries. But it was just this one that he won it for. So what he found is this, that when you have low level or low energy light, you don't see electrons shooting off. It's only when you have higher energy light that this happens. And so you can put red light on certain metals and you don't see electrons jumping off. But if you put green light on there, electrons do jump off. Not very fast, but they do. Put on blue light, they jump off very fast. And we know that red light is lower energy than green light. Blue light is highest energy light.
So is blue stuff or blue metal supposed to shine more than like red metal?
Not necessarily. It doesn't translate to that. So whenever we have any kind of light in the room, it's white light, right? And white light contains all the frequencies. So white light contains red, blue, and green, right? Now, if we see blue though, what does that mean? It means that it's absorbed red and green and given off blue light. So it doesn't transfer that would be what was happening. Like those are 2 different things. Now the kind of metal, whether it's, say aluminum or magnesium, they hold onto electrons differently. So the electrons are held on more tightly in certain metals than less than other metals. So based on how tightly they're held onto also will determine what happens in the situation. But yeah, more blue light being emitted onto the metal piece, the more electrons are going to be transferred off. Maria?
So does blue light, does that like damage your eyes?
It can, yeah, because it's high energy. So it's more about the brightness that will damage your eyes, not so much the blue, but how bright it is. Now, you probably have heard this before, to avoid blue light when you're about to go to bed. That's because if you have a lot of blue light, that's high energy light, your brain thinks it's daytime. You see, your brain it determines whether to go sleep or awake based on light outside. So if you're exposed, so if you're in the morning, if you're really tired, if you go outside in bright light, that really helps you wake up, because your brain now knows, okay, I need to wake up. But if you stay in darkness all day long, you're gonna be really sleepy, because melatonin is secreted in your pineal gland, which basically tells you to go to bed. And so at night, it depends upon your age and your routines, but let's say at 10 p.m. at night, melatonin is secreted. And melatonin doesn't really make you sleepy necessarily, but it tells you it's time for bed. And your body starts to shut down and get ready for bed. But if you then look at your phone, which has lots of blue light on it, melatonin stops being secreted. Your body thinks it's daytime again, and you don't get sleepy, and it's hard to fall asleep. So blue light can disrupt your sleeping patterns because you don't get melatonin like you need to fall asleep.
So, like all computer screens have blue
Yeah,
light?
all computer screens. So you can get filters on it that will block out the blue light.
What about glasses?
Yeah, you can also glasses can also do that.
No, mine's not that.
Yeah, so certain glasses can also block out blue light.
What is it, like, what are we talking about whenever you say wave model?
Say again?
The wave model thing?
Mhm.
What's that?
So wave model just thinks of light as a wave. And so wave model just thinks of light as moving in a wave.
But who made it?
Oh, different people. I mean, there wasn't just one person who made it.
Is it the one we use nowadays?
It's tricky because now what we think of is that light has two natures to it. That light has a wave nature and a particle nature. And so in some ways, light can act like a wave. In other ways, that it can act like a particle. And so we say that light has both a wave nature and a particle nature to it. Emma?
The little yellow things that are going off, are those electrons?
Yes, those are electrons. So what also they realized with this is that even intense light, even very, very bright red light, could not eject electrons in this situation. So it didn't matter how bright the red light was or how long it's shown on the middle piece, you could not eject electrons from red light. So what does that mean? Well, it means that it's not acting like a wave in that situation. If light were purely a wave, then the brighter the light, the longer it was shown on, it should eventually eject the electrons, and it didn't.
So when people are making like photos, is that why they use like red light? Because it's not as bright?
Oh, you mean like when they're like in a dark room and they're yeah, so a red light would have less energy, and so it wouldn't damage the film as easily as blue light would.
So can't most animals not see red lights?
Depends on the animal. I haven't heard about most not seeing red
Like
light.
hogs can't see red.
Mhm.
I don't think. Do you? I don't think
Yeah.
they can see red light.
Interesting.
Whenever people like will go hunting, they'll use like red flashlights.
Oh, okay, interesting.
Because animals can't see it.
Okay, well, I'm sure some can, just maybe not lots of them. That's interesting. I know that a lot of animals, so you have in humans have 3 cone cells, so that give you color: red, green, and blue cone cells. And so if you don't have red cone cells, you don't see any red. So it's possible that animals don't have red cone cells, but I know a lot of animals have better night vision, and so probably in place of that red, they probably have more rod cells, which give them night vision. So I would imagine that's probably what happens. They trade seeing red for having better night vision. But also in this experiment, even dim blue light and dim green light could eject electrons. And so those results showed that light is not just a wave. Light is more than just a wave. and it was strange to think about at the time, but light is not just, so when you think of it as a wave, that means there's no particles, it's just pure energy. So light, they thought of as just a wave of pure energy with no particles, no mass. But what Einstein showed is that even though light does not have any mass, it acts like it does. It acts like it has particles that make it up in certain situations.
How could it have, like, how does it act like it has mass?
Yeah, it's strange. We can't explain it fully, but energy can
How
be,
does it act like it has mass?
it shoots off electrons. So basically it's like like a pool ball that hits another pool ball. When it hits metal, what happens? It ejects electrons. And so in that sense, it's like a particle.
For the last 2 points, are they like contradicting each other? Is it-
No, because what that said is that for red light, so for that middle one, even intense red light could not eject electrons, but dim light that was blue or green could. That's what it's saying, is that the intensity of light, whether it's dim or bright, did not have an effect on it. It was the wavelength, the color of the light is what made it transfer electrons. So what Einstein said with this experiment is that you have to think of light and all kinds of radiation as having 2 natures, a wave nature and a particle nature. Now, these are contradictory to each other. You can't have both a wave and a particle at the same exact time. It's one or the other at different situations. So what he said is to think of light as a stream of packets of energy. And so it's pure energy still, but the energy is in the form of packets called photons. And those packets are kind of like particles. So a photon is a particle of radiation with no mass that carries a quantum of energy. So before we look at the equation that said energy of quantum equals h times frequency, Einstein revised that equation to say this: energy of a photon equals h times the frequency. So in your notes, with this equation, you should know that Einstein is the one who made that new equation, and you should make a note of that. Basically, it's just a way to to use this equation in different situations, not just one situation.
But they're both still correct.
They're both correct. It's just that he just revised it to apply to other situations like light beams. And so what he said is that energy in a photon of light has to have a certain energy value to cause the ejection of an electron. And if it's below that value, it can't move the electron off the middle. Energy is tied to the frequency or the color of the light.
And H is still,
Planck's constant. Yeah, it's the same thing. Yeah, so it's always the same number.
And we don't know who came up with the first one?
Say again?
We don't know who came up with the.
Oh, Max Planck was one of, I mean, there was a lot of people who talked about that, but you could say, Max Planck would be the primary one who made that equation up. So if you want to write down a scientist for the first one, Max Planck would be the one to write down for that. We'll get to that tomorrow. We'll get to that today. So let's do the last slide for today. So for homework for the rest of the class, about 15 minutes to go. On page 143, do 5 through 7, and then go into the next page and go up to number 14. So basically do 5 through 14, starting on page 143 today for homework. And tomorrow we'll do more of chapter 5.1. I'll show you a short video. We'll do a lab. We'll do with different kinds of color fire, so it's gonna be a fun lab.
What page is it on?
Page 143, do 5 through 14. Page 143.
Miss Holly. Miss Holly.
Turn the lights back on.
Does it mean when it has S? Oh, that means 1/2. Oh. Sorry. Yes, it means the same. Okay. Oh.
Put it in the container.
Word. For 5, it would just be this number times H, right?
Yes,
Okay. Smart.
Is H, the constant?
exactly.
Keep clearing your memory. You gotta do this.
Okay, I know. Oh, you just.
Would the, answer be in joules per second?
And so that would cancel that second right there, and so you just have joules.
Is that always going to be joules?
Right.
And then the unit for the answer.
Basically, like.
4.19. Wait, Mary got some numbers for me. 6.96. You should get that. Yeah. Sure. We don't need to know how far it is. It's 4.50. Projected wavelength. Wait, what was it? For this one, it gives us the wavelength and the temperature.
You don't have temperature.
Okay. So it gives you the wavelength and you're trying to
So you have to
find.
use two equations. So you have to use the equation yesterday.
Yeah, that's what I was
Yeah, the
thinking.
speed of light equals 50 times the wavelength vector solve for signal to approach, then and be careful because nanometers you have to convert to meters.
How many
Why is that one so complicated?
Nanometers is a billionth of a meter. So multiply the activity in 9 and it'll be 8 meters.
by a night?
10 to the negative.
Oh.
That's gonna be negative 7.
So
4.50 times 10 to the negative 7. Oh wait, no. Instead of 7. 11. It's gonna be 11.
So this is just going to here.
Because nanometers has to get bigger. 11 is bigger than 2. No, but you're going to meters. Yeah, like 12 inches is 1 foot.
Because you have to convert wavelength.
4 should be wrong. It has to be small. Nanometers. Yeah. 4 point. You were right.
I'll write on the board.
But it's going to be 10 to the second plus. Like 10 to the second.
So what you would do, so what is it, 4.5, what's the number?
Yeah, 1.5.
So it's 4.50 times 10 to the second nanometers. So if you see nanometers, it's 10 to the 99 meters. So basically what you do is this.
It'd be negative 7 and not 11. It has to get smaller.
That's right. So on the board, it shows you how to convert from nanometers to meters.
I'm just gonna put You can already see like that.
So what you convert it to, would you? No.
Because you can see the line.
So. Why did that come out for you?
Because basically what you need to do is cross the meter of the earth.
Good.
Oh, it gives us
Door.
wavelength,
See.
which we have to find the frequency. And then
So once you get frequency, then you go back.
Now C equals the speed of light. There we go. All right.
what if you divide it by
C divided by.
and then you get the frequency?
Wait, you gotta put this on.
No. So it's the wavelength times the percent.
So it's not.
Yeah.
Okay, 105. Times H. Oh, shoot, I put that in.
There's on this one.
4.42. E to the negative 36.
Trust me, my calculator is right. But usually not.
4.4. Okay, what was it? 4.42 e to the negative 36.
I don't want to. Okay. Get C. But you still have C saved? Now divide that. Okay, C divided by 0.125 meters. We don't have to put it at equals. And then that's the, no.
Number 6, so.
And then multiply that by
Right.
Wait, do we do? Do we do 8?
No.
Oh, that's right. Wait, what? No. Some of the numbers were, you're 40, you're 20 something. Like that. You're 1.6 times 20.
Maybe I typed in like.
Or we could do 4.42 times 10 to the negative 36. Did you get that?
No.